Have you ever wondered how casinos manage to steal your money? How they rig their games in such a way that it does not feel rigged even when it is? This is because they are experts at probability and expected value. In this video, we take the first step beyond the definition of a random variable. We talk about its expected value. This enables us to make the predictions in financial analysis. Last time we said, a random variable is a way to assign a number to each possible outcome of some random situation. This could be the daily return of a portfolio, the loss on a position, or a 0-1 indicator of default. Now we ask a new question. If a random variable can take many values, which value should we think of as its typical value? Which single number should we use to summarize it? In probability theory, this typical number is called the expected value. We often write it as E of X. There is a simple rule behind this name. Take all possible values that X can assume. For each value, you know two things: the value itself and the probability that X takes this value. To get the expected value, you multiply each value by its probability. Then you add up all these products. In symbols, many books write E of X equals the sum over all values of X times probability of X. If this looks strange to you, it is enough if you remember the sentence. The expected value is a probability-weighted average of all possible values. Now let us connect this general rule to finance. We take X to be the random return of a portfolio between today and tomorrow. For each scenario tomorrow, there is a portfolio return in dollars or in percent. And there is a probability for that scenario. If we apply the same rule as before, we get what people in finance call the expected return. Mathematically, it is just the expected value of the return random variable. Now we look at a very simple example. We start with only two scenarios for tomorrow. Scenario 1. The portfolio gains $10. Scenario 2. The portfolio loses $5. At first, we assume that both scenarios are equally likely. So the probability of the gain is 1/2, and the probability of the loss is also 1/2. Now we apply the formula for expected value. In this scenario, the expected return is plus $2.5. This means over a long period of time, you should average a gain of $2.5 per day. Now change only one thing. We keep the same two scenarios, but we change the probabilities. Suppose the gain of $10 happens with probability 1/3. And the loss of $5 happens with probability 2/3. So now the expected return is exactly 0, even though the loss is more likely than the gain. The larger size of the gain offsets its lower probability. This example shows something important. The expected value is not the same as the most likely outcome. In our example, the loss is the most likely scenario, but the expected return is 0. So far, we have treated expected value as a weighted average. Now we add a second way to see it. As the best possible single prediction for the random variable. Imagine again that the random variable X is the daily return of a portfolio. You want to summarize this whole distribution by one constant number A. You know that this prediction will almost never be exactly right. The realized return will usually be higher or lower than A, sometimes by a little, sometimes by a lot. So you need a way to measure how wrong a prediction is. A natural measure is the squared error. You take the difference X minus A and then you square it. Small errors become tiny. Large errors become very large. And the result is always non-negative. This is important because it prevents errors from cancelling each other out. Now imagine you look at all possible outcomes of X. For each outcome you have a squared error, X minus a squared. You use the expected value rule again. You average these squared errors with probabilities as weights. You get the average squared error of the prediction A. The question is, which constant A makes this average squared error as small as possible? It turns out that there is a unique best choice. That choice has a name we already know. It is the expected value of X. If you are interested in the underlying math, I will leave a link to some material in the description. So we can say, the expected value of a random variable is the single constant that is least wrong on average. Least wrong in the precise sense that it minimizes the probability-weighted average of squared deviations. This is one reason why expected value is so central in finance. Whenever you quote one number as the return you expect, you are often implicitly using this optimality property. Let us summarize. If you represent portfolio returns as random variables, the expected value is the first thing you ask for. What is the expected return of this strategy? You can think of expected value in two ways. First, as a probability-weighted average of all possible values, where probabilities act as weights in the average. Second, as the best single constant prediction for the random variable. Best in the sense that it minimizes the average squared deviation between the prediction and reality. In the next video, we will keep the expected value as our anchor. We will then look at variance and standard deviation. These will tell us how much a random variable tends to fluctuate around its expectation, and how this fluctuation connects to the financial idea of volatility and risk of loss. Thank you for watching.